तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Welcome back to Prestressed concrete structures. This is the first lecture on design of members. In this lecture, first we shall study the calculation of demand in a member. Next, we shall move on to design of members for axial tension. Under that, we shall study the design of the prestressing force and then the analysis of ultimate strength. Next, we shall move on to design of members for flexure. First, we shall study about the calculation of moment demand, and then today we shall wrap up with the preliminary design. We shall be using some geometric properties in the analysis and design of members for axial tension. On the left side, we see the cross section of a typical member prestressed for axial forces. The total section is represented by A. This section is broken up into three components. The net area of the section with concrete is represented by AC. The area of the reinforcing steel, which is non-prestressed, is represented by AS, and the area of prestressing steel is represented by AP. Thus, A is equal to AC plus AS plus AP. We shall use another definition, which is the transformed section. The transformed section means it is an equivalent section of concrete and it is larger than the original cross section A, and it is calculated as AT is equal to AC plus the ratio of the moduli of the steel and the concrete times the area of the non-prestressed steel plus the ratio of the moduli of the prestressing steel and concrete times the area of prestressing steel. Thus, we calculate the transformed area for an elastic analysis of a section where the material is same throughout, which is concrete. First, we shall study of the design of members, some general ideas. For design of prestressed concrete members, we follow the limit states method as given in section 4 of IS 1343/1980. First, the force demand in a member under the design loads is determined from a structural analysis. A preliminary size of the member is assumed for analysis. Next, the member is designed to meet the demand. If necessary, another cycle of analysis and design is performed. That is, the first step, even before we start the design, is an analysis. And it is in an analysis of a structure, we get the demand in each of the members. Now, the following sections will help us to understand how to calculate the demand in a member under the design loads. In the limit states method, the design loads are calculated from the characteristic loads by multiplying them with load factors which are represented as gamma f. Several types of loads are considered to act together under selected load combinations. The load factors are included in the load combinations as weightage factors. The demand in a member for a particular type of load is obtained from the analysis of the structure subjected to the characteristic value of the load. The demands for the several load types are then combined under the load combinations based on the principle of superposition. Thus, when we say that several types of loads are acting on a member, we first consider the principle of superposition, which is based on a linear analysis for each type of the load. To calculate the total demand in a member, we first analyze the structure for each type of the load and then combine the forces within the member by the load combinations. Now, these load combinations have the appropriate load factors as weightage factors. Once we combine the forces under the load combinations, we get the total force demand in a particular member. Next, let us study that for a particular type of load, a characteristic load is defined as the value which has a 95% probability of not being exceeded during the life of the structure. This concept assumes a normal distribution of the values of the type of loads. When we start the analysis, we pick up the characteristic value for a particular type of load. The characteristic value is defined as the value which has only 5% probability of exceedance. That means 95% of the time the load will not be exceeded, and this assumes a normal distribution of the values of the load. In this sketch, in the x axis we are plotting the values of the load, in the y axis we are plotting the frequency. Now, in a normal distribution, we can find out the mean, and we can also find out a value of the load which has 5% probability of exceedance. This value of the load is called characteristic value, and we first start with this characteristic value to come to the design load. Now, from where do we get the characteristic loads in an analysis? The characteristic loads can be obtained from IS 875-1987, which is the code of practice for design loads for buildings and structures, and IS 1893-2002, which is the criteria for earthquake resistant design of structures, as follows. That means we have two main codes which gives us the characteristic values of the different types of loads. The first is IS 875-1987, and next is IS 1893-2002. The several types of loads are given in these codes as follows. The dead load, which is represented as DL, is given in IS 875 in part 1. The live load, which is also sometimes referred to as the imposed load, is given as IS 875 part 2. There is a subtle difference between live load and imposed load, that if a part of dead load does not act throughout the life of the member, if it acts only at certain periods, then that part of the dead load can also be included as imposed load. It is up to the discretion of the analyst to consider whether a fraction of dead load is imposed or not. Next, we can calculate the wind load, which is represented as WL from IS 875 per 3. We can calculate snow load, which is represented as SL from IS 875 part 4. The earthquake load, which is represented as EL, that is obtained from the separate code, which is IS 1893 part 1. For special loads, there are some guidelines in IS 875 1987 part 5. In addition, specialized literature may be referred to for these loads. The special loads are listed below: temperature, hydrostatic, soil pressure, fatigue, accidental load, impact and collision, explosions, fire. Thus, we see that for the special loads, IS 875 part 5 give us some basic guidelines, but we may need specialized literature or international codes to get more detailed values for these special loads. For special situations, the loads are determined from testing of prototype specimen, like dynamic load tests, wind tunnel tests, shake table tests are some type of tests to determine the loads on a structure. Finite element analysis is used to determine the stresses due to concentrated forces and dynamic loads. If we are looking for specialized structures like nuclear containment structures, then the loads given in the codes may not be adequate. We may do some specialized study or experiments to calculate the characteristic loads or the design loads for the particular type of structure, and we can conduct special type of experiments like dynamic load tests or wind tunnel tests or shake table tests to get the loads acting on the structure. A finite element analysis can also be used to study the stresses for a concentrated load, or also we can study dynamic loads by the finite element analysis. Hence, we understand that for general purpose we have the codes, but if we are analyzing some special structures for special situations, we may have to do special studies or we have to do experiments to get the loads acting on the structures. Next, the load factors and the combinations of the various types of loads are given in table 5 of IS 1343-1980. The following are the load combinations for the ultimate loads: 1.5 times dead load plus live load, 1.2 times dead load plus live load plus minus wind load, 1.2 times dead load plus live load plus minus earthquake load, 1.5 times dead load plus minus earthquake load, 1.5 times dead load plus minus wind load, 0.9 times dead load plus minus 1.5 times earthquake load. Since both wind load and earthquake load can act in either direction horizontally, we are using a plus minus sign convention in the load combinations. Thus, we have two groups of load. One is the gravity load, which is the dead load, live load or snow load, and we have the lateral loads, which are the wind loads and earthquake loads. There are special type of loads like hydrostatic or soil pressure, which are also lateral loads. The load combinations for service loads are as follows: dead load plus live load, dead load plus 0.8 times live load plus minus earthquake load, dead load plus minus earthquake load, dead load plus minus wind load. Thus, we have two sets of load combinations. The first set is for the ultimate loads with higher load factors. The second set is the service loads which have load factor equal to 1 for most of the cases. In some cases, even the load factors are less than 1 when the chances of live load and earthquake load acting at their characteristic values simultaneously is less. In such a situation, the load factor is less than 1. In some cases, the dead load may help in the stability of the structure. In such a situation, a reduced load factor is used for the dead load even for the load combination under ultimate loads, and there we use a load factor of 0.9 for the dead load, which is specifically meant for the problems of stability. Regarding analysis of structure, IS 1343-1980 recommends the same procedure as stated in IS 456-2000. A structure can be analyzed by the linear elastic theory to calculate the internal forces in a member subjected to a particular type of load. Thus, the code allows us to use the linear elastic theory for the analysis even if we do the design based on the limit states method. Now, for design, there can be more than one way to design a member. In design, the number of unknown quantities are larger than the number of available equations. Hence, some quantities need to be assumed at the beginning. These quantities are subsequently checked. The design of a member is not a straight-jacketed procedure. It depends on the person and his or her preference. There are more unknowns than the available sets of equations. Hence, we need to assume some variables first, solve the set of equations, and then check whether the assumed values are appropriate or not. If they are not appropriate, then we need to do this cycle once again. The members can be designed either for the service loads or for the ultimate loads. The procedure given here for a particular type of design is one of the possible procedures. The design is based on satisfying the allowable stresses under service loads and at transfer. The section is then analyzed for the ultimate capacity. The capacity should be greater than the demand under ultimate loads to satisfy the limit state of collapse. This is different from what we had studied for reinforced concrete. For reinforced concrete, the design is based on the ultimate strength being greater than the demand under ultimate loads. But for prestressed concrete, we are adopting a different approach. We are designing a member such that the allowable stresses under service loads and at transfer for the concrete are satisfied. And next, we are checking whether the ultimate strength of the member is greater than the demand under the factored ultimate loads. Thus, first we do the design based on the service loads, and next we do an analysis for the ultimate strength and compare that strength with the demand under ultimate loads. Next, we are moving on to design of members for axial tension. Prestressed members under axial tension only are uncommon. Members such as hangers and ties are subjected to axial tension. Members such as piles may have bending moment along with axial compression or tension. In this figure, we see an hanger where the forces only in the vertical direction has been shown. Now, this hanger can be pre-stressed to have no tension under the service loads. First, a preliminary dimension of the member is selected based on the architectural requirement. The prestressing force at transfer, which is represented as P0, should be such that the compressive stress in concrete is limited to the allowable value. At service, the design prestressing force, which is represented as PE, should be such that the tensile stress in concrete should be within the allowable value. The amount of prestressing steel AP is determined from the design prestressing force based on the allowable stress in steel. Thus, the steps are that a preliminary dimension of the member is based on the architectural requirement. Then we calculate the maximum possible prestressing force that can be applied in the member based on the allowable compressive stress at transfer. The design prestressing force is calculated from the stresses at service loads, and this stress should not exceed the allowable tensile stress value. After designing the prestressing force, we calculate the amount of prestressing steel, which is equal to the design prestress force divided by the allowable prestress in the tendons. What are the equations that help us to calculate the stresses in the member at transfer and at service? At transfer, in absence of non-prestressed reinforcement, the stress in concrete, which is denoted as Fc, is given as follows. Fc is equal to minus P0 by AC. Here, AC is the net area of concrete that we had studied earlier, and P0 is the prestress at transfer after short term losses. We are denoting the negative stress for compression. If we have non-prestressed reinforcement in addition to prestressing tendon, the stress in the concrete can be calculated as follows, where Fc is equal to minus P0 divided by AC plus the ratio of the moduli of the steel and concrete times AS. AS is the area of non-prestressed reinforcement, ES is the modulus of elasticity of steel, and EC is the modulus of elasticity of concrete. Thus, here we have two expressions for the calculation of the stress in the concrete at transfer. We have a simpler expression if there is no non-prestressed reinforcement, and if there is non-prestressed reinforcement, then we have a more accurate expression which involves the moduli of the two materials. Next, we are moving on to the analysis of stresses for service loads. At service, the stress in concrete can be calculated as follows. Fc is equal to minus Pe by Sc, which is the effect of the prestressing in the concrete, and plus minus P divided by At. Here At is the transformed area of section, P is the external axial force. In the equation, plus is used for tensile force and minus is used for compressive force. Pe is the effective prestress after long term losses. In this expression, we did not consider the non-prestressed reinforcement. If there is non-prestressed reinforcement, AC is to be substituted by AC plus ES divided by EC times AS, and AT is to be calculated including AS as we had seen during the definition of the geometric properties. Thus, we find the stresses at service loads as a combination of the stress due to the prestressing force and the stress due to the external axial force. Next, once we have designed the member for the stresses at service loads and satisfying the allowable stresses at transfer. Next, we move to the analysis for the ultimate strength. The ultimate tensile strength of a section, which is represented as PUR, is calculated as per clause 22.3 of IS 1343/1980. The ultimate strength should be greater than the demand due to factored loads. In absence of non-prestressed reinforcement, the ultimate tensile strength of a section is given as PUR is equal to 0.87 times FPK times AP. Thus, here we are saying that the code limits the maximum tensile stress in the prestressing tendon to 0.87 times the characteristic tensile strength, and hence the maximum tensile strength of the section is given as 0.87 times the characteristic tensile strength times the area of the prestressing steel. That any tensile capacity of concrete is neglected at the ultimate limit state. If there is non-prestressed reinforcement along with prestressing tendons, then the expression of PUR is equal to 0.87 Fy times As plus 0.87 Fpk times Ap. Fy is the characteristic yield stress for non-prestressed reinforcement with mild steel bars, or it is the characteristic 0.2% proof stress for non-prestressed reinforcement with high yield strength deformed bars, and Fpk is the characteristic tensile strength of prestressing tendons. Thus, we have the expression of the ultimate tensile strength of a member with or without non-prestressed reinforcement. Let us now see this design method from an example. Design a post-tension hanger to carry an axial tension of PDL is equal to 300 kilonewton. The dead load includes the self weight, and PLL is equal to 130 kilonewtons. The dimensions of the hanger is 250 by 250 millimeter square. Design the section without considering non-prestressed reinforcement. The grade of concrete is M35. The age at transfer is 28 days. Assume 15% long-term losses in the prestress. The following properties of the prestressing strands are available from tests. Type of prestressing tendon is 7-wire strand. Nominal diameter is equal to 12.8 millimeters. Nominal area is equal to 99.3 millimeters square. Tensile strength Fpk is equal to 1860 Newton per millimeter square, and modulus of elasticity is equal to 195 kilonewton per millimeter square. Before we start a design, we have done the analysis to find out the forces due to the dead load and live load, and here we have also estimated the force due to dead load by including the self weight. We have estimated the long term losses in the prestressing tendon. The material properties are selected based on the materials that we are using. We know the characteristic strength of concrete, and we know the properties of prestressing steel, which can be available from tests or from the catalogs of the suppliers of the prestressing steel. First, we are doing a preliminary calculation at transfer. We are assuming that the area of concrete is almost equal to the total area, which is equal to 250 times 250 is equal to 62,500 millimeter square. Next, we are calculating allowable stress for M35 concrete under direct compression at transfer. As per the code, FCC allowable is equal to 0.8 times the allowable stress for compression under flexure, the allowable stress for compression under flexion is given as 0.51, the instantaneous strength for M35 concrete, and substituting the values of the FCI, which is 35 after 28 days, we get FCC allowable equal to 14.3 Newton per millimeter square. Thus, at transfer, the allowable compressive stress for M35 concrete is 14.3 Newton per millimeter square when the prestress is transferred at 28 days. The allowable prestressing force P naught is given as FC times AC, which is equal to 14.3 times 62,500, which is equal to 892,500 newtons. Thus, we have found the upper limit of the prestressing force that can be applied at transfer. Next, we are doing the preliminary calculations at service. There we are assuming AT is equal to A equal to 62,500 millimeter square. The stress in concrete can be calculated by this expression which we learned in the modulus of analysis of members. FC is equal to minus PE divided by AC plus P divided by AT. From the definition of the problem, allowable stress at surface FCT allowable is equal to 0 Newton per millimeter square. That means we are not allowing any tension under service loads. Considering 15% loss, the effective prestress is expressed as 0.85 times the prestress at transfer. Once we substitute the values of FCT allowable and PE in the above equation, we get this equation where we have A, the area of the section, as the approximate value both for AC and AT. Now, solving this equation, we find 0.85 times P0 is equal to P, which is the external load. Thus, P0, the required amount of prestressing force at transfer, is equal to the external load divided by 0.85, which is equal to 506 kilonewton. With the allowable prestress tendon being Fp0 equal to 0.8 times Fpk, we have the allowable prestress in the tendon equal to 1488 Newton per millimeter square. Thus, we have found the required prestressing force at transfer, which is equal to 506 kilonewton, and we have also found the allowable prestress in the tendons, which is equal to 80% of the characteristic strength, which is equal to 1488 Newton per millimeter square. Thus, the required area of the tendon is equal to AP equal to 506,000 divided by 1488 is equal to 340 millimeter square. Select 4 strands with AP is equal to 4 times 99.3 is equal to 397.2 millimeter square. Thus, we have calculated the required amount of the prestressing steel, and we have selected the number of strands that we need to apply the prestressing force. The prestressing force at transfer P0 is equal to the area of the prestressing steel times the allowable stress, which gives P0 equal to 591 kilonewtons. Thus, the required prestressing force was 506 kilonewtons, but we can apply a slightly higher prestressing force because we had used approximate values of AC and AT in our calculations. Next, we are doing the final round of calculations with the accurate values of AC and AT. The final calculations at transfer are as follows. AC is equal to 62500 minus 397, which is the area of the prestressing steel, is equal to 62103 millimeter square. This is the accurate value of AC. Then the stress in concrete at transfer is equal to minus P0 by AC. We are substituting the actual value of P0 that we are going to apply, the accurate value of AC, and we find FC is equal to minus 9.5 Newton per millimeter square. We find that this value of FC is less than the allowable compressive stress for M35 concrete at transfer, and hence we can say that the pre-stressing force is proper and the stresses at transfer are within the allowable value. Next, we are doing the final calculations at service. EP is equal to 195 kilonewton per millimeter square, EC is equal to 5000 root over the characteristic strength, which is 35, which comes out to be 29,580 Newton per millimeter square. Thus, we can calculate the transformed area. AT is equal to the area of the concrete, which is 62,103, plus the ratio of the two moduli 195 divided by 29.6 times the area of the pre-stressing steel, which is 397.2, which gives us AT is equal to 64,720 millimeter square. Thus, you find that the AT is larger than the total area A. The stress in concrete due to service loads is given as FC is equal to minus PE by AC plus P by AT. Once we substitute the values of PE, which is equal to 85% of the pre-stress at transfer, and we are substituting the external force as 300, the dead load, plus 130, the live load, and we are substituting the accurate values of AC and AT, we find that the stress in the concrete is minus 1.4 Newton per millimeter square at service. Thus, there is no tensile stress in concrete under service loads, and it satisfies the objective of the design. We are doing the final calculations for the ultimate strength. The ultimate strength is given as 0.87 FPK times AP, which is equal to 0.87 times 1860 times 397.2, which is equal to 643 kilonewtons. Now, the demand under the factored loads equal to PU is equal to 1.5 times 300 plus 130, which is 645 kilonewtons, and here we find that PUR is almost same as PU, and we need not have to define this design, and we can consider this design to be correct. Thus, the design cross section is that the dimension of the section is 250 by 250. We are placing 4 7-wire strands with a pre-stressing force of 591 kilonewtons, and we are providing nominal non-pre-stress reinforcement for thermal and shrinkage cracks. This section satisfies the allowable stresses at transfer, and at service there is no tensile stress generated in the concrete, and at ultimate the demand is equal to the capacity. Next, we are moving on to the design of sections for flexure. Now, for flexure, how do we calculate the moment demand? For simply supported pre-stressed beams, the maximum moment at the span is given by the beam theory. That means we have the expression from the beam theory of the maximum moment that comes at the span. For continuous pre-stressed beams, the analysis can be done by the moment distribution method. The moment coefficients in table 12 of IS 456-2000 can be used under conditions of uniform cross section of the beams, uniform loads, and similar lengths of span. That means the code IS 456 allows us to use moment coefficients to find out the moments at the span and at the supports for a continuous beam, provided we satisfy certain conditions. And if we satisfy those conditions, then we can use those coefficients directly, and if those conditions are not satisfied, then we have to do an analysis based on the moment distribution method. The design is done for the critical section, that means the section which has the highest positive moment or negative moment, and for a simply supported beam, the critical section is at the midspan when there is a uniform load throughout the beam. For a continuous beam, there are two critical sections at the supports and one critical section at the span. That means for a continuous beam, we have to look not only at the span but also at the supports, and we have these three critical sections. Usually the higher of the two moments at the two supports is taken for the design of both the ends. For design under service loads, the following quantities are known: MDL, which is the moment due to dead load, which does not include the self weight, and MLL, moment due to live load. Thus, from the analysis, which is either by the moment distribution method or by using the moment coefficients, we find out the moment demands at the critical sections, one for the dead load, which is represented as MTL, and another for the live load, which is represented as MLL. We may not know the moment due to self weight yet, because the section may not be available during the analysis. The following quantities are unknown: the member cross section and its geometric properties. We do not know what the size of the member is or what type of member is. The other unknown quantities are AP, the amount of prestressing steel, PE, the effective prestress, and E, the eccentricity. Thus, our unknown quantities here are in fact more than our available set of equations. We do not know the self weight moment or the geometric properties of the section. Also, we do not know the variables related with the prestressing. We do not know the amount of prestressing steel or the effective prestress or the eccentricity of the CGS at the critical sections. The material properties are selected before the design. That means before we design a member, we should know what are the materials that will be supplied by the contractor, and hence the material properties need to be selected before we start the design. For design of sections for flexure, we have a two-stage procedure. The identification of these two stages is for a clear understanding of the design procedure. As I said before, that the design procedure that is presented here is just not the unique, it is one of the several possible ways. We are designing for the service loads, making sure that the allowable stresses at transfer and at service are satisfied. Next, we are doing an analysis for the ultimate strength and making sure that the strength is greater than the demand under ultimate loads. The design steps are divided into two groups. One is the preliminary design and next is the final design. In the preliminary stage, the cross section is defined and the effective prestress and the area of the prestressing steel are estimated. In the final design, the values of E, the eccentricity at the critical section, PE and AP are calculated. The stresses in concrete at transfer and under service loads are also calculated. the stresses are checked with the allowable values. If required, the section is modified to satisfy the allowable stresses, and then we check for the ultimate strength. Today we shall cover only the preliminary design, and in our next class we shall move on to the final design. For the preliminary design, the steps are as follows. Select the material properties FCK and FPK, which are the characteristic values for the concrete and the prestressing steel. Determine the depth of a beam, which is represented as H. The depth can be based on architectural requirement, or the following empirical equation can be used. H is equal to 0.03 root over m to 0.04 root over m. Here H is in meters and m is in kilonewton meters. M is the total moment excluding self-weight. The selection of the depth of a beam usually is governed by the architectural requirement depending on the headroom clearance that is required. But if the architectural requirement is not given, then we may start with a preliminary estimate of the depth of the beam based on the empirical equations. Now we need to check this again in our final design whether the depth is adequate or not. The third step in the preliminary design is to select the type of section. Now there can be several types of sections depending on the application. We shall learn more about them in a subsequent lecture. For a rectangular section, which is the simplest type of section, we can assume the breadth B is equal to half times the total depth. Calculate the self-weight or estimate the self-weight to be 10% to 20% of the load carried. Calculate the total moment MT including the self-weight. Here we are denoting the moment due to self-weight as MSW. Once we have estimated the total moment, which is equal to the MDL plus MSW plus MLL, we are calculating the lever arm, which is also an estimate for the preliminary design. The lever arm Z is roughly equal to 0.65 times H if MSW is large. That means if the self-weight moment is say greater than 30% of the total moment, then the design is governed by a lever arm which is roughly equal to 65% of the total height of the beam. If MSW is small, then the lever arm can be taken as half of the total depth. Once the lever arm is estimated, we can estimate the effective pre-stress that we need to carry the total moment. Remember that in a pre-stressed concrete beam, when the moment is applied, the compressive force shifts up from the CGS by a distance of Z, and the pre-stressing force does not change much within the service loads, and we assume that the pre-stressing force is staying constant, and hence the moment applied is equal to the pre-stressing force times the lever arm by which the compression shifts from the CGS. From this concept, we can calculate the effective pre-stress equal to the moment divided by the lever arm. If the self-weight moment is large, then the total moment governs the effective pre-stress, and we express PE is equal to MT divided by Z. If the self-weight moment is small, then the moment due to imposed loads governs the design, and we estimate PE is equal to MIL divided by Z. MIL is the moment due to imposed load, which is equal to the total moment minus the moment due to self weight. Thus, we have some preliminary guidelines to calculate the total moment, then we calculate the lever arm from which we calculate the effective prestressing force. The 8th step is considering the effective prestress equal to 70% of the characteristic tensile strength of the prestressing steel. Calculate area of prestressing steel AP is equal to PE divided by FPE. That means at this stage we are estimating the area of the prestressing steel based on the estimate of the prestressing force and the effective prestress. We are doing a check on the size of the section, the average stress in concrete at service. Average stress means that the stress which occurs at the CGC, that is given as C by A, which is equal to the effective prestress divided by A. This average stress should not be too high as compared to 50% of the allowable compressive stress FCC allowable. Since the FCC allowable occurs at one extreme edge of the member, the average stress should not be too high than 50% of this FCC allowable, and this average stress occurs at about half the depth. If it is so, then increase the area of the section to A is equal to PE divided by 0.5 FCC allowable. That means once we know effective prestress, we can just increase the area of the section to make sure that the average stress is within 50% of the allowable value at service. Thus, today we started to learn about the design of members. First, we studied how to calculate the demand in the member. We know that as per the limit states method, we need to have the characteristic loads to start with. The characteristic loads for dead load, live load, wind load, snow load are available from IS 875. The characteristic load for the earthquake is available from IS 1893 part 1. For special load situations like hydrostatic, soil pressure, fatigue, accidental loads, explosion, there are some basic guidelines in IS 875, but we may need special literature to get the values of these loads. In special situations, we may have to do tests to get the loads acting on the structure. The tests can be dynamic loads or wind tunnel tests or shake table tests. We may also do a finite element analysis to get the stresses due to concentrated forces or dynamic loads. Once we have got the characteristic loads from the codes, then we analyze the structure by a linear elastic method, and we calculate the force demand due to a particular type of load. We combine the force demand for this particular type of load with other demands for other types of loads by the load combinations, which has the load factors as the weightage factor for each type of load. We studied the two sets of load combinations that are available. For the ultimate loads, the load factors are usually greater than 1, and for the service loads, the load factors are usually equal to 1. Now, once we have combined the forces for each of the load type based on the load combinations, we can get the total force demand in a member either for the service loads or for the ultimate loads. Next, we proceed for the design of the member, and the design can be several ways. One way is that let us try to satisfy the allowable stresses at transfer and at service. That means the design is primarily based on the service loads, and then let us check the ultimate strength, which should be greater than the demand under the ultimate loads. This design procedure is different from the design procedure of reinforced concrete, where we design for the ultimate strength to be greater than the ultimate load demand directly. Next, we moved on to the analysis and design of members for axial tension. First, we saw how to design the prestressing force. We calculate the maximum possible prestressing force at transfer based on the allowable stress in concrete at transfer. Next, we calculate the design prestressing force at service based on the allowable tensile stress at service. Now, we need to make sure that the design prestressing force is such that the prestress at transfer is less than the value calculated based on the allowable stresses at transfer. Finally, we check the ultimate tensile strength of the member, and this should be greater than the ultimate load demand. We solved a problem for the design of an axial member under tension. It is a hanger which is subjected to dead load and live load, and it was designed only for the prestressing steel. First, in our preliminary calculations, we assume the area of concrete and the transformed area to be same as the gross cross-sectional area. Based on the allowable stress at transfer, we found out the upper limit of the prestress at transfer. Next, based on the allowable tensile stress, which was 0 for this problem, we found out the required prestressing force for the section, and we found out that the required prestressing force is less than the allowable prestressing force at transfer. We found that the ultimate strength of the section was almost similar to the demand under ultimate loads, and like that we finalized the section. Even if we have prestressing steel, we provide non-prestressed reinforcement for thermal and shrinkage cracks, and if there is some shear, then we also need to provide stirrups accordingly. Finally, we moved on to the design of members for flexure, and there we first learned about how to calculate the moment demand. For simply supported beams, we pick up the expressions of moment demand at the span for a uniformly distributed load or a point load. If it is a continuous beam, then we may use the moment coefficients provided in IS 456, the applicability of which is based on certain conditions of uniform cross section of the beam, similarity of the span lengths, and uniform loads. Most of the time these conditions are satisfactory, and hence we can use the moment coefficients. If these conditions are not satisfied, then we have to go for a more rigorous analysis based on the moment distribution method. Now, once we have done the analysis, we find the demand at the critical sections. For a continuous beam, the critical section is at the span and also at the supports, and once we have the demand, then we proceed for the design of the member. Now, the design of member under flexure is more involved. We have identified two stages of design, first the preliminary stage and next the final stage. In today's lecture, we covered the preliminary stage, where we estimated the amount of effective prestress, the amount of prestressing steel, and we also estimated the cross section. In our next class, we shall move on to the final design, where we shall recalculate all these values and make sure that the stresses at transfer and service are within the allowable values, and also the ultimate strength is greater than the demand under ultimate loads. Thank you.